So in this lecture, we will talk about the fastener static analysis for tensile loading only. In this particular case, you can think that when I have loads, I have a load applied, okay? This load that's applied is going to translate into two loads, okay? I will have a load here. We're going to call that load taken by the bolt PV. And because this is in tension, you can expect this to be in compression, right? So you're going to have a load PM here. Okay, the same is the load on both sides, is PM. So, um, so when you're solving these problems, you want to make sure this is always engaged. Okay, you want this to be always touching. You don't want this to be loose. So immediately you can see that this can never, this can never be bigger than zero. And if it's just barely equal to zero, that's the moment where they're barely touching each other, but there is no preload applied to the problem then. Okay, so typically this has to be less than zero, has to be in compression for the tension bolt to actually be carrying the load. Okay, and PT then is the total tensile load acting on the problem, and we typically the bolt acting load acting on one bolt is the total tensile load divided by the number of bolts. Okay. Okay, so the total load will be equal to P is equal to PV over PM. This is bolt. This is bolt, and this is members. Okay, the load taken by the members. And then this is preload. Okay. And the preload, so the total load then acting, the bolt load, if we have the preload, will be PV plus FI. The acting in the member will be PM minus FI. And then if we think about this, P is equal to this, right? And let's work our equations a little bit here. And then you have a deflection. The total deflection here has to be the same deflection there. The deflections are the same because this is the same system. Doesn't make sense this would contract more than this. There has to be the same. So therefore, we're going to equate both equations. And then from here, we can say this is equal to this. And then if I replace this in this equation, I can rearrange this. And if you remember from a previous class, this was your joint stiffness constant. Okay, that's a C. So in other words, I can express everything. You can rearrange this as follows. Everything can come in the following form. This has to be less than zero. Remember what I told you? It has to be less than zero, because you want to make sure this is in full contact. And the tension bolt is doing its job. Okay. Then the second thing we want to do is once we have our loads analysis, we want to apply our design factor. Here, the standard design factor is 1.2. You want to maintain that every single time. Some companies have 1.15, 1.5, 1.4, different applications. So this is the base. And remember, if you have any additional factor, then you will multiply this times this. Okay, so this is important. Just remember, as we did for the case of springs. So now we move on. Once we multiply our load, now we can just use P applied. And please note that you do not apply, you don't apply the design factor to your preload. The preload is a design load. It's something that's already designed, embedded in the bolt. And once it's done, it's done. There's no approximation to that. There's a set value. You know what it is. Okay, and then this stress, the total stress, axial stress acting on, at the bolt, inside the bolt is FP over AT. Where does my AT come from? If you remember table 8, 8.1, 8.2, this is your AT. And if you're using the core series, then it's this one right here, depending on what type of bolt you're using. And if it's course, fine. If it's English or it's metric. But these values are already given and tabulated for you. Okay? So now we move on. The design, you want to design against joint separations, as I told you. And the way we do this is, and if you think about this, right, you want you want to make sure that this is, when this is equal to zero, p sub zero is equal to this. Okay, so what we do is we say we calculate n sub zero or n separation, and we divide this by your preload, that's fi divided by applied, your p sub zero, that's equal to this. Okay, and then you divide the p sub zero by the applied load, or fi divided by p applied 1 minus c. And you want to make sure this is bigger than this. Okay. In another way, so this is one check. The very first check you need to do is make sure that your bolts are in contact. There's no separation. The second check you have to do is proof strength. Proof strength, then instead of using yield, we use your proof stress. Okay, that's what we use for this analysis. And then this is the questions that we always do. This one, you don't have to worry about this. This is automatically satisfied because this is the load factor given in the design. And sometimes the load factor is not given and you ask what is going to be the load factor we're going to use in the problem, then you can evaluate this. Okay. So the summary, 3 checks. This is your M. I was talking about earlier when I just mentioned that there was a small m. So when you do these problems, uh, m can equal to 1 or can equal to 1.17. This right here is assumed that you already multiply the load by 1.2, or this is already multiplied by that standard 1.2 or any design factor that you have. So this is 1, this is 1.17 for pressure system applications. And then the strength of the tensile bolt is a second check, and this has to be bigger than 0. You want to check for yield strength, and that has to be bigger than 1.15. This is important that you see this is not 1. Okay, so these 2 checks have to be done and made sure that we comply and we agree with them. Okay, the separate checks, typically you might think, oh, if I just apply this, I should be good enough. But no, look, yield is 1.15, it's not 1, so you have to look at that. Just as a review, just remember what tables you use to find ultimate yield, tensile strengths, and proof load. That comes from table 8.9 to all the way 8.11. And that gives you your yield strength, gives you your ultimate strength, and gives you your proof strength. If you want to find what is should be recommended, a preload in a high tensile application, then this could be the recommendations. However, sometimes this is already given in the problem by the designer. This is how much preload we apply, and that should be good enough. You have to keep this in mind that when you're doing this and you're down out there in the field, you design how much is the preload. We as engineer, we specify, we say what this should look like. Okay, so this summarizes all the analysis for static analysis for tensile loading, bolts of the tensile loading, and next we will just do an example to wrap these topics.